So therefore we come to another long derivative. Then if I take the gradient of the potential, which is a vector, then I will multiply this to a rotation to transform from local to ITRF. Then when you come to ITRF, you have polar wobble at time t. You will consider nutation. You will consider precision, and you will consider one rotation with the gas angle, and the result will be the vector or acceleration in let me write this here, CRF or geocentric CRF. So as you see, from the spherical harmonics or from the potential, you can come to this acceleration in the space by this 5 transformation. The first one from the local to ITRF. These 3 change, these 4 change this terrestrial frame coordinates or acceleration to the acceleration in the celestial frame, the place that the satellite is moving there. So that's the principle for this transformation. Transformation, I write it here, from local frame to CRF generally. Celestial reference frame. So then we know the relation between satellite acceleration and the gravity field of the Earth. So what is that? It's simply I can write it in that form. If you consider the spherical harmonic coefficient, spherical harmonic series from 0 to infinity, R over R, and M minus N to N, V and M, Y and M, theta and lambda. If you take the derivative, what is the gradient? Gradient of V will be the derivative of V with respect to R, derivative of V with respect to R theta, and derivative of V with respect to R sine theta and d lambda. So that's all. Derivative of V with respect to R will be minus 0 up to infinity n plus 1 over R n plus 1 minus n to n V and M Y and M theta and lambda. V respect to R and theta will be summation again, and I have this R over R again, M, 1 R behind as well. Then I can write R here. Yes, that's correct now. R, store, big R, V and M, and here I have derivative of the spherical harmonic with respect to theta, and the last one, R sine theta will be, I will write 0 up to infinity 1 over Rn plus 1 summation m minus 1 v and m y and m theta and lambda sine theta. So we have the derivatives or the gradients of the potential, which are the acceleration in the local frame. Then you can do those transformation to bring it to the terrestrial frame. But by the way, you can consider that each series starts from 1 because, as we already discussed, the 0 degree harmonic does not exist in this formula for derivatives because it's constant laterally. Then when you take derivative with respect to theta and lambda, this will be 0. So even if it is 0, it's fine, but it will be is fine in the series because it doesn't affect that. So then we have the derivatives and this one. So therefore, simply this gradient, I will write it and draw the formula. I draw a figure for you. If this is the Earth and this is the satellite moving around the Earth here, the satellite, the accelerate this local frame is like that at satellite level, and this point has a coordinate, the inertial frame, which is Z CRF, celestial frame, and here is gamma vernal equinoxes, and Y CRF, which is right hand side. And also we have another frame, and here let me draw this. This one is a gamma, and here is this Greenwich meridian. Greenwich meridian, and then when we consider that, then it is of course here I have the always let me change the color. Z CRF. Then we have another like this, and we have X of TRF here and Y TRF here. And the first thing is to change this coordinates from local to this TRF, and from TRF by those movements of the rotation we come to CRF.